Hello again, everybody. Welcome back. So we've been talking in this chapter about how rotational kinematics, values like theta and our omega, that is our rotational velocity, and our alpha, our rotational acceleration, are very similar to linear kinematics, one-dimensional or two-dimensional, moving in just the x direction or the x and y direction. So there's a lot of correlations to that. But the one difference is the fact that objects moving in circular paths, well, those circular paths may vary depending on the radius. Let's see, two circles, actually I'll make them concentric to save some space right here. We have a circle right here. All right, it may, an object may go in a circle in a certain amount of time, and then another object may go in the same circle but with a greater radius, and also the same amount of time. All right, those people who run track. All right, if you want to get around a track in the least amount of time, you run on the inside lane, the inside path. You don't run on the outside lane. All right, so even though both of these objects have undergone one revolution in the same amount of time, and they have the same rotational velocity, they're going to have very, very different linear velocities, or what we call tangential velocities. This is what we talked about way back at the beginning of the year with linear velocity. But your actual velocity, the speed with which an object is moving, if it were to shoot off in a straight line, so that one right there, and I'll change colors right here. Come on now. Oh, I need to, okay. This one right here, if for some reason the object were to shoot off in a straight line, the blue would be going a lot faster because it would have a greater tangential velocity than the red one would, even though they do have the same rotational velocity. And that's all due to the fact that they have different radii, or radiuses, you could say. I guess radii is the right way to say it. So if right here is the center of our circle, that radius for the blue one is clearly greater than this radius for the red one. Not very centered, but you get the idea. Make a great big black dot in the middle. All right, that's our center right there. So we say that the tangential velocity, the linear velocity we might say, is equal to the radius times the angular velocity. All right, now remembering which side of the equal sign the r is on sometimes can get confusing to students. So and it does to me sometimes. So in order for me to remember. To remember that, I always think that the two English letters, the V and the R, are never directly next to each other. All right, the R is either multiplied by our omega, our angular velocity, or if we were to solve for omega, the omega would be the tangential velocity divided by the radius. All right, but the two English letters, V and R, are never directly next to each other. So that's how to convert from our linear velocity, or you might say our tangential velocity, this guy and this guy right here, to our angular velocity. All right, so the angular velocity will be the same for both of these circles, but the linear velocity will clearly be different. And it's all a result of the different radii. Now we've talked about centripetal acceleration already. We had a chapter on uniform circular motion. All right, and if an object is moving in a circle, like that, all right, well, something is being directed towards the center in order to keep that object in a circle. We called it centripetal force. But of course, centripetal force, force is mass times acceleration, so we said the centripetal force is really mass times centripetal acceleration. So this directed towards the center is some sort of acceleration, or I should say what's centripetal acceleration, but it's an acceleration directed towards the center. In fact, if you recall, that's what centripetal means, center seeking. All right, so that even if an object is moving at a uniform rate in a circle, it's still experiencing an acceleration. A force is being directed towards the center. A force is being applied to that mass towards the center right there. All right, and this equation comes from the fact that if you recall our equation for in uniform circular motion for centripetal acceleration, AC, was v squared over r, right? Well, if v, that is our tangential velocity, our linear velocity, you can call that vt if you want right there, if we square this, that would be r omega squared, or really r squared omega squared, over r. All right, and so the r's, of course, well, the r and the r squared cancels out, and so we simply have centripetal acceleration is r times r times our rotational velocity squared. That's where that comes from. You may also recall, it may also be helpful to remember if you're solving for things like time, that centripetal acceleration equals 4 pi squared r over t squared. I meant to make that a capital T. T squared. All right, and it's also centripetal acceleration is equal 4 pi squared r times our frequency squared. But they're less helpful because they don't have tie-ins to our rotational velocity. This one does, because there's a very direct relationship between tangential or linear velocity and rotational velocity. So we simply made that substitution, and now we have an equation for centripetal acceleration in terms of our rotational velocity omega. And even though up to this point we've talked about and we've defined rotational acceleration, we haven't really applied it very much. It's the rotational acceleration alpha is related to the linear acceleration, all right, or tangential acceleration by r, very much in the same way that our omega is related to our linear velocity by way of r as well. But we haven't really applied this very much because, if you recall, in our chapter in uniform circular motion, the reason it's called uniform circular motion is that we do have a velocity in a circle. Oh, worst circle ever. We do have a velocity in a circle, but that velocity was constant. Let's try this one more time. I think I hit the bottom of my writing area right there. Not much better, but that's supposed to be a circle right there. All right, and so you can have a centripetal acceleration, but have a constant velocity around the edge. What this is saying here is that there is not just a centripetal acceleration, but there's also a linear acceleration. So if that were to shoot off in a straight line right there, it would be greater here and greater here and even greater here and so forth. So you might say it's like it's like a linear acceleration, but directed in a circle. So to find our linear acceleration, our tangential acceleration, we simply take the radius, all right, so this being our radius right there, and multiply it by our rotational acceleration. And of course, rotational acceleration and rotational velocity and rotational displacement are all related using the same kinematics equations that we had for linear values. But this is simply the conversion between linear value, rotational value, linear value and rotational value. But then this means, and we're going to look at this in just a second, that, give me a red marker right here, red pen, here we go. If an object is moving in a circle, it has centripetal acceleration. And if it's moving in a circle and speeding up faster and faster and faster and faster, it also has a tangential acceleration. So this is directed at right angles to the path of motion. So like all these arrows are right here. It's our tangential acceleration. Centripetal acceleration is directed towards the center. So I'll write a T right there. So let's make an object. I'll make the object, I don't know, green. At this point right here, the object is experiencing two accelerations. It's being accelerated towards the center, centripetal acceleration, but since it's going faster and faster in that rotational path, it also has a tangential acceleration. So what we're going to need to do is take these two acceleration components and combine them into a single acceleration, and we're going to do that in just a minute or two, okay? But to point out real quick, just kind of restate the fact that linear velocity and acceleration and rotational velocity and acceleration are different. Let's take a look at this one picture real quick. So this is a turntable, right? And on this turntable, I guess it's a piece of construction paper, and it's got some tape or something like, or no, I guess it's, oh, they look like those magnetic letters, all right? They're E's right here, okay? What is the same about these two E's? Well, they both have the same rotational velocity. Oops, that's not really directed toward the center, is it? They both move through the same angle, you might say, in a certain amount of time. That angle and that angle are the same. It's kind of hard to draw them because our E's are blurred right here. But the one on the outside is not getting around the edge of the circle any faster than the one on the inside, right? You might say that this, angular velocity right there is going to be the same as this angular velocity here. So the angular velocities are the same. Angular velocity 1 equals angular velocity of 2. We'll call this 1 and this 2 right here. But what is clearly different? What is clearly different? Why is there more of a blur right here than there is there? Well, even though they have the same angular velocity, they do have different radii, right? The radius to this guy is out there, and the radius to this guy is right there. Clearly different radii. And so that's going to result in a different multiplier of our angular velocity, which is going to give us different linear velocities. So that means that our linear velocity of 1, is going to be, oops, I'm about to draw my greater sign the wrong way, less than the linear velocity of 2, which is why you see more of a blur right here, because in the same amount of time, again, this picture, there's a certain amount of time that it suggests because the shutter of the camera was open for a certain amount of time. In a certain amount of time, this object 2 has to swing through a much greater distance because it's got a greater radius than this guy right here. You'd see even less blur if we move this guy closer to the center because you'd be decreasing the radius. All right. So while the linear the rotational or angular velocity is the same of both of these E's, both of these letters, the linear velocity would clearly be different. So if for some reason they were to shoot off in a straight line, that would be velocity of object 2. This would be, I don't know, the velocity of object 3. They are also offset as well. They're not exactly on a straight line going out. But this one definitely has less of velocity than that right there. And this is also a setup to our example 7. And this is conceptual right here. It's basically the same thing. All right, we've got 2 children on a merry-go-round. Like you might see at an amusement park or something like that. Question A asks us, is the angular speed of child 1, so this guy in the red shirt, is child 1, and the purple shirt is child 2, greater than, less than, or same as the angular speed of child 2? Well, they had the same angular speed because, and these guys actually happen to be in the same line. They're kind of lined up radially right there. In the same amount of time, the girl, child 2, moves from there to there, and the boy moves from there to there. It's the same angle in the same amount of time. So angular velocity 1 equals angular velocity 2. But clearly one child is going to be experiencing greater linear speed. So heaven forbid one of them were to let go of one of their horses. Or both of them were to. This guy right here would have a linear speed that is what? Greater than, less than, or equal to that of child 2. It'd be greater than, right? Child 2 is moving at a lessened tangential velocity or linear velocity. So velocity of child 2 is going to be less than velocity of child 1. So I guess I answered that backwards. Child 1 is greater than child 2. That's why if the further out you are to the edge of the carousel, it's going to be more difficult to hold on to your horse because you're moving at a greater speed, at a greater velocity in this, I might say a greater linear velocity in this circle right here. Same rotational velocity, different linear velocities. All right? I'm just going to show you these last 2 pictures real quick, and then we'll and then we'll call this quits for this segment. Centrifuges. We're going to be talking about centrifuges, and in fact, we have in the past with uniform circular motion. We talked about how this thing right here is a astronauts go in it and they experience 2, 3, 4, 5, 6, 7 Gs sometimes and get used to all those forces. Centrifuges are also used in medicine, what these little vials do. And you'll notice, by the way, that the ends, the pointy parts of the vials go in there, and they actually kind of point outwards. They don't point straight down, but they point outwards towards the outside of that centrifuge. These things spin up to ridiculous speeds, and so doctors can test how forces affect medicines and the ability for them to combine and that kind of thing. But whereas before we talked about centrifuges in terms of simply uniform circular motion, here now we're going to be talking about circular motion that gets faster and faster and faster and faster and faster. I know that wasn't a very good illustration of that, but we have accelerated motion, not just radially. Nope, it's a really bad radial value. Not just radially, centripetal acceleration, but also centripetally and tangentially as well. And that's what I'm going to start the first segment off with. That's what I'm going to start the next segment off with when we start up again. All right? So thanks for following along, and make sure you ask me any questions if you have any, and I'll see you on the next one.